So we've moved on to part B of our asteroid in an ellipse problem, and part B says that at point A, our asteroid is 1.5 times 10 to the 10th meters away from the center of Earth. And as well at point C, our asteroid is 2 times 10 to the 11th meters away, and it wants us to calculate the force of gravity at both of these points, and then the perpendicular change in momentum and the force of uniform circular motion at both of these points as well. So of course what we're going to do first is just to calculate the force of gravity at both of these points. So Newtonian gravitational force, of course, is equal to the big G constant times the mass of Earth times the mass of our asteroid divided by the distance from our asteroid to Earth squared. And reviewing the information that we've been given, we have the mass of our asteroid and then the distances from our points from the center of our asteroid at both of these points to the center of Earth. And as well, we've been given the mass of Earth, just a simple thing we can look up on Google, but it's been supplied to us so we can spare ourselves the trouble. So basically all we have to do is to plug in the given values so that we can calculate our gravitational force at both of these points. So if we do point A first, we can just plug in all of our values. So the big G constant is 6.67 times 10 to the negative 11th times the mass of Earth, which is 5.97 times 10 to the 24th, and then times the mass of our asteroid, 1.2 times 10 to the 15th kilograms, all divided by the distance from point A to the center of Earth being 1.5 times 10 to the 10th squared. And all we have to do is calculate this value. Just simply plugging it in, plugging all our numbers in, and what we end up with is 2.12 times 10 to the 9th newtons. So at point A, we have this magnitude of gravitational force, which is acting on our asteroid. And when we focus on point C, we can expect that our force value, our gravitational force value, will be less than the one that we have just gotten, because our asteroid is going to be much further away from Earth. And of course, dividing by a bigger distance will give us a smaller value. So let's hope that our prediction will give us, at point C, will give us the right value. So again, just plugging in these values, 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th times the mass of our asteroid, 1.2 times 10 to the 15th, and then all divided by our secondary value at point C, the distance being 2 times 10 to the 11th squared. And again, we just need to plug these into our calculator, and it looks like we end up with 1.19 times 10 to the 7th newtons, which indeed did end up less than our other value at point A. And so what we need to do now is we need to find the perpendicular change in momentum value as well as the force of uniform circular motion. And actually this first one here, the perpendicular change in momentum, is a lot easier to find than we would expect, because if we remember from part A, we drew the net force vectors at points A and C, and when we ended up drawing our perpendicular change in momentum vectors, they were equal in magnitude to the net force vectors. And this is also going to be true for the quantities at these points. So really our perpendicular change in momentum is going to equal these values at both of these points. So now all we need is the force of uniform circular motion. And what we can actually do is use the same logic as with this perpendicular change in momentum. Also in part A, we talked about how the force of uniform circular motion was kind of this anomaly that happened at points A and C because we didn't have any parallel change in momentum. Our motion was completely perpendicular to the net force. So what we're basically implying here is that when we have the force of uniform circular motion at these 2 points, it is going to equal the net force, which is equal to the gravitational force, but only at these 2 points. So as well as the perpendicular change in momentum being equal to our gravitational force at A and C, so will our uniform circular motion force. So all 3 of these values are going to equal each other, but only at points A and C. So this evaluation was a lot easier than we thought it would be. So we just need to remember that at the ends of the ellipse, when we have this moment of uniform circular motion, the uniform circular motion value will equal the perpendicular change in momentum as well as the force of gravity. And it's very much worth it to remind ourselves that the uniform circular motion at these 2 points isn't something we can calculate on its own because it's not true uniform circular motion. It's just pure coincidence, really, that this uniform circular motion can even have a value that we know just because it is in an ellipse. But otherwise, we have finished the problem. That is it for the asteroid in an ellipse problem.